This is the second half of lecture 21, in which we look at the flow of fluids. In this part of the lecture, we will think about what causes liquids to flow. So again, we are looking at very simple cases. We have liquids that preserve their volume flowing in pipes, and the motion is laminar. There is no turbulence. So first of all, I want to start by reminding you that if you have a particle, and if this particle moves with constant speed, then there doesn't really have to be any external reason why this particle moves with constant speed. So the motion with the constant speed doesn't need to be maintained, and it can happen even if there are no forces or if the forces are balanced. Something similar is happening with the liquids as they flow through a pipe. If you have liquid and if it flows through a pipe with constant velocity, so velocity here is equal to the velocity here, then there doesn't really have to be any force difference, any net force acting on a small part of this liquid. When we talk about liquids, we prefer to use pressure rather than the force because it's a more convenient quantity to use in these cases. So to rephrase what I just said in terms of pressure, if you have a flow of fluid and if this flow maintains the same velocity, then the pressure here must be the same as the pressure here. If, however, the velocity of your liquid changes, so let's say you were moving with some velocity v, let's say small, and now we are moving with velocity v large, then if you look at this small particle, it was moving with a small velocity, now it's moving with a large velocity. So some sort of acceleration must have happened somewhere in between. And to have acceleration, you must have some sort of net force pushing from left to right. And because of that, the conclusion here is that the pressure in this section of the pipe must be higher than pressure in this section of the pipe. Otherwise, you wouldn't have excess force and you wouldn't have this particle moving with higher velocity. There would be no acceleration. So this line of reasoning leads to a conclusion which is sometimes a bit counterintuitive, that if you have a flow of liquid that changes the velocity, then you have more pressure where the flow is slower and less pressure where the flow is faster. So in case of a pipe, pressure is high here, pressure is low here. So wide parts of the pipe have higher pressure than low parts of the pipe. And if we reverse the situation, if we have something going through a narrow pipe that widens at some point, then you have water moving with higher velocity here, v1, with lower velocity here, v2, so v1 is more than v2. And if this particle, small imaginary pocket of water, was moving with high velocity, and now if it's moving with less velocity, then some sort of deceleration must have happened here, somewhere in between, which means that there must be a net force acting from right to left. So pressure here, P2, must be higher than pressure here, P1. So if V1 is more than V2, then P2 must be more than P1. So that's how pressure and the change in velocity are related. Now I want to think a little bit about gravity, because the thing is that if we are near Earth and most of our pipes are near Earth, then there is always gravity. So let's think about what happens, how does gravity affect flow of water. So let's start by thinking about simple cases. I will have the simple case of a droplet of water moving down in gravity, and it's obvious from here that if this droplet of water is moving down, then it will gain speed. So V1 will be less than V2. And the opposite is true. If you're moving up, then you lose your velocity. Now, if gravity is the only thing, then this is what happens. But sometimes you have some combination of gravity and pressure. So now, instead of a moving particle, let's think of an example of a liquid that's not moving. So let's say you have this tall container where you have some liquid, and this liquid isn't moving. And let's think about what happens with the pressure. So if you read the lecture 20 material, then you know exactly what happens to the pressure. If I have gravity pointing down, then I have more pressure here than down here than up there. So P2 is more than P1. So if we forget about velocity and the motion, the effect of gravity is that you have more pressure as you go lower. So we have two effects here. One effect is that gravity causes increase in pressure, and the second effect is that gravity causes increase in velocity. And when we are in a more complicated situation where you have gravity and both the pressure and the velocity are changing, then things work out in the following simple way. So it turns out that the gravity, the pressure, and the velocity obey a simple equation. And this equation is that if you follow a stream of water, then pressure plus half of water density times its velocity squared plus water density times g times y, where y is the depth, is constant. Okay, so if you add this combination of the pressure and the velocity and the depth, this combination will always remain the same. Or in other words, if you have some sort of a flow where your velocity changes and your elevation also changes, and you have different pressures applied here and here, then let's say this is 0.1 and this is 0.2, then this combination, P1 plus 1 over 2 rho V1 squared plus rho G Y1 will have exactly the same numerical value at 0.1 and 0.2. So at 0.2, if I add the pressure, half of rho velocity squared plus rho Gy, I will get exactly the same number, even though the pressures, the velocities, and the elevations may individually vary from 0.1 to 0.2. You can think about this law, which is called Bernoulli law, as kind of a conservation of energy, and it does follow from the conservation of energy. You probably have already noticed that this term kind of looks like kinetic energy, and this term kind of looks like a potential energy. And so basically this quantity has to be conserved, and the conservation means that if one of these quantities goes up, then something else must go down to compensate. So for example, if you are at 0.1 and then you get to 0.2 and there is some sort of liquid flowing, and if your pressure is higher at 0.2 compared to 0.1, then one of the following two things has to happen, or both of them could happen. You are either flowing with less velocity at 0.2 compared to 0.1, or you went down in elevation. Your y is lower at 0.2 compared to 0.1. So in the first case, if your velocity dropped, that kind of makes sense. You're moving from low pressure to high pressure, and this high pressure is slowing you down. Or if you have a pipe that goes from a higher elevation to a lower elevation, that also makes sense. You're moving down, and because of that, there is effect from gravity, and you have more pressure here compared to there. And of course, both of these things could be happening simultaneously. You could be at the same time moving from a higher position to a lower position, and your velocity could be dropping at the same time. The important thing is that when you add up these three constituents of Bernoulli law, you should be getting exactly the same number at point 1 and at point 2. So these things are best understood by examples. Let's move to question 21.1 then. This is on slide number 8. And on this slide, what you have is you have drawing of a pipe that looks like this. You have section 1, then you have section 2, which is wider, and then you go down like so. And then here you have section 3, which is about as wide as section 2, and then you have a very wide section, which is section 4. And so there are two questions. First question is, in which section does the stream have the highest speed? And the second question is, at which point, to which section does the stream has the highest pressure? So I want you to pause this video here, think about this, and then continue watching the video and check your answer. Okay, so I hope you had time to think about this. Let's start with the first question. Where is the velocity highest? Where do you have the fastest flow? This, I think, is a simple question because you don't really care about what this pipe does. The only thing that you care about is its width. We know from the first half of this lecture that since the volume is conserved, you have the fastest flow where you have the narrowest pipe, and the narrowest pipe is here in section 1. And therefore, my conclusion is that you have the highest velocity in section 1. And consequently, you have the lowest velocity, the slowest flow in section 4. Now let's think about the pressure. To figure out the pressure, we would have to write the whole Bernoulli equation. So Bernoulli equation tells you that pressure plus half of rho v squared plus rho gy is conserved. So this combination is the same in sections 1, sections 2, 3, and 4. Let's start by comparing sections 1 and 2. So sections 1 and 2 are at the same level. So this term is kind of the same for sections 1 and 2. But section 1 has higher velocity, which means that for this quantity to be conserved, section 1 must have lower pressure. So the first conclusion is that pressure 2 is higher than pressure 1. Now let's think about sections 2 and 3. Let's compare them. How do sections 2 and 3 compare? For sections 2 and 3, what you have is they are of same width, so they have the same velocity. Velocity of your stream is exactly the same or almost exactly the same in sections 2 and 3. What's different is the y. You have less y in section 3. Section 3 kind of goes down. And from here, I conclude that you have more pressure in section 3. Since this quantity needs to be conserved, if you have less of this, you must have more of that. Okay, so the conclusion is that pressure at point 3 is higher than pressure in section 2. Now, you can do exactly the same. You can apply exactly the same reasoning to sections 3 and 4. So this is kind of similar to what we did for sections 1 and 2. You have the same y. The stream doesn't go up or down. And in section 4, you have a slower motion, so you must have higher pressure. You will conclude that pressure at 4 is more than pressure at 3. So overall, our overall result, the final result, is that the highest pressure is at section 4. And this is happening for two reasons. Both reasons work to increase the pressure. The first reason is that you are lower, so you have less of this term. And the second reason is that you're also moving slower in section 4. So for this quantity to be conserved, your pressure has to be higher than in other sections. So this was kind of a simple example. Now what I want to do is, for the rest of this lecture, I would like to solve two sample problems. They are on slides 9 and 10. I will start with the problem 21.2, which is problem 90 from your textbook. What's happening in this section is that you have a sewage outlet, there is a house, and there is a slope. This is the street level. This is the street level. And then you have sewers 2.16 meters below the street level. So 2.16 meters below the street level. They tell you that density of sewage water is about 1,000 kilograms per cubic meter. So this is how dense, how heavy the cubic meter of the water is. And the question is, what's the question? Yeah, the question is that you have to find the minimum pressure that must be created by the pump to transfer waste of average density of 1,000 kilograms per cubic meter from the outlet to the sewer. And sorry, I forgot to tell you that the outlet is here, it's 6.59 meters below the street level. So basically what you have to do is you have to pump something from here to here. And the question is, what's the minimum pressure that will let you do this? So why don't you pause here, try to solve this, work on this, and then if you get stuck, if you can solve it, that's great. If not, if you get stuck, then unpause the video and watch my solution. To solve this problem, what I will do is I will use the Bernoulli law. I will call this point 1, and I will call this point 2. Bernoulli law tells me that if I write pressure plus half of rho v squared at point 1 plus rho gy1, this will be equal to the same quantity computed at point 2, so half of rho v2 squared plus rho gy2. So let's start with terms that are simple. I think these two terms are simple. I know y for both. So here I will have 1,000 times 10 times 6.59. And here I will have 1,000 times 10 times 2.16. Sorry. And I want to put a negative sign both here and here, because this was my 0 level, and I'm below 0 level, so I need minus signs in both cases. Now, what about the velocity? So V1. V1 is the velocity of sewage as it enters this pipe. I will make an assumption that this fluid isn't really, the sewage water isn't really flowing. It doesn't have any energy to start with, and you have to lift it purely by performing work with the pump. So V1 I will set to 0. And for V2, I will also assume that as I'm lifting this water, it's not going to stream out with high velocity from this pipe. What I'm doing is I'm just lifting it up to here, and then it kind of sits here, or maybe slowly moves. But V2 I will also set to 0. And so now this problem becomes quite simple. I'm looking for a pressure difference, and for the pressure difference between points 2 and 1, I will have my pressure at point 1 minus pressure at point 2 is equal to 1,000 times 10, which is 10,000, times 6.59 minus 10,000 times 2.16. So this is 10,000 times 4.43, and this is 1, 2, 3, 4, 44, 300. The unit of pressure is Pascal, 44,300 pascals of pressure. So the sign here kind of makes sense. And it makes sense because I need to have more pressure here compared to there at point 1, so that this pressure difference drives sewage water up and against gravity. Okay, so now I want to move to the final problem, problem 21.3. This is problem 71 from the textbook, and it's actually one of your homework problems. So I'm not gonna completely solve it, but this is one of the more complex problems, so I thought I would give you some hints. So what's happening here is that we have this reservoir, and we have a hole some distance h from the top. The depth of this is h capital, and we have, of course, since there is a hole, we have water streaming out. This water will, as it exits the reservoir, it will move on a parabola because this is a simple projectile motion, and it will hit the ground some distance x away from the wall. There are 3 questions. The first question is, what's distance x? Find x. The second question is, where should I drill a second hole so that the stream of water ends up at exactly the same x? So h2, such that I get the same x. And the third question is, this is the most interesting question, at what depth should I drill a hole so that this x is maximal? So I think it's clear that if my hole is like right here, then my stream of water is under higher pressure, but it doesn't have enough distance to go far. And if my hole is at the very top, then there is not much pressure, so it's not going to go very far because its exit velocity is low. There must be some sort of golden middle, which is not necessarily in the middle, that gives me the most distance traveled horizontally. So what I will do is what I want you to do is I want you to pause this video, think about this, and then unpause this video and compare your solution to mine. Okay, so as I said, I'm not going to completely solve this problem, but I will at least partially solve it. So first of all, what I want to do is I want to forget about these holes. I want to see I want to find the exit velocity of water, of the stream of water, if the hole is some distance h away from from the very top. To find velocity of my stream as it exits here, and I think this is kind of the first step, is I think the most tricky step conceptually. What I want to do is I want to write down again. I want to write down my Bernoulli's law. So my Bernoulli's law tells me that pressure at point 1 times rho g y at point 1 plus half of rho b squared at point 1 is equal to pressure at point 2 plus rho g y at point 2 plus half of rho b squared at point 2. So first of all, I will think what's happening. How does this point at the very top compare to this point, which is just behind the hole? So here, when I compare these 2 points, point 1 and point 2, what I have is in both of these cases, I have liquid that's not moving. So I will ignore this part. And then I will have a pressure difference at point 2. My pressure will be pressure at point 1 plus rho density of water times G times Y1 minus Y2. And if you think about this, Y1 minus Y2, this is Y1, this is Y2, is exactly H. So pressure at point 2 is equal to the pressure at point 1 plus rho times G times H small. So this is not surprising. This simply tells me that if I go from here to here, if I go deeper into my container, my pressure will increase by the factor of rho times G times H. Now what I want to think about is I want to think about what happens as this water under pressure exits. So this is point 2 behind the hole, and this is point 3 just outside the hole. So I think it may be worth rewriting this equation. And so what's happening now is that Bernoulli's law still holds, but now I have a liquid that moves. So my V2 is 0 because when I'm behind this wall, I'm not moving yet. My Y, how high I am, is the same. So Y2 and Y3 are the same. These two will cancel each other out. And now what I have is I have half of rho V3 squared equal to P2 minus P3. Pressure 2 minus pressure 3. And now I think this is the key thing here. I notice that pressure here is the atmospheric pressure because I'm now outside of this container. So pressure at point 3 is the same as pressure at point 1. So pressure at point 3 is the same as pressure at point 1. I have pressure 2 minus pressure 1. And from this equation on top, pressure 2 minus pressure 1 is rho G times H. I will cancel rho from both sides, and I will get my velocity at point 3, which is the exit point, to be equal to the square root of twice G times H. So this formula kind of seems familiar if you remember kinematics and projectile motions and energy conservation. This is usually the velocity that you get when you drop something from height h. And so what's happening here is that this water stream is exiting the hole as if it was an object that was dropped from this height. So since I ran out of space, I will erase this derivation and I will keep this formula down here. So I know that my exit velocity is square root of twice gh. Now, if I know my exit velocity, can I compute how far away will I end up from the wall? And the answer is that I can, because this motion right here is a projectile motion. And for this projectile motion, I have two equations. One equation is that horizontally, I'm moving with constant velocity, and the distance I travel, x, is equal to my velocity times time. So the more time goes, the further horizontally I move. And then I also have a vertical motion. So this distance from here to the ground is h capital minus h small. And when I hit the ground, h capital minus h small must be equal to g times t squared divided by 2. So what I will do is I will find my time from here, and it will be the square root of 2 h capital minus h small divided by g. I will substitute it here, and I will get my distance to be equal to my velocity, exit velocity, which is square root of twice gh, times the square root of twice h capital minus h small divided by, what's this number? This is g. Yeah. So this is our main equation. Let's circle it and let's look at it and see what it tells us. So first of all, unless I made a mistake, which I don't think I did, this g cancels out with this g. There is no g in this equation, which means that I will get exactly the same result on Earth and on Moon. So g doesn't matter. You get more pressure on Earth because of higher g, but then you also drop faster on Earth. And on Moon, you will have less g, so less pressure, but you drop slower. So in the end, those two effects cancel out, and you end up exactly at the same position. So the formula for x is the square root of 4, which is 2. So let me put this 2 outside of the square root, times h capital minus h small. So this is the formula. This is how x depends on h small. And the question is, question C, the most difficult question is, which h will give you the most x? And if you know your calculus well, then you know exactly what to do when you have a function. And when they ask you to find its maximum, what you do is you take a derivative and you equate your derivative to 0. So dx dh equal to 0 is the equation that you want to solve. Okay, I will stop here. I want to remind you again that we have Zoom help room sessions every Monday, Wednesday, and Friday from 12:30 to 2:30. You can join those Zoom sections. If there is something in the lectures that you don't understand, you can ask. If there is something in the homework that's too difficult or you don't understand, you can ask. If there is anything in the studio problems or the lab that you cannot do, you can ask about that. I'm kind of repeating this because many of you don't do that, and that's fine. I mean, if you feel okay with the material, if you're doing well, then you don't have to join the Zoom help room. But if you're struggling with the material, if there is something that you don't understand, and if you complain about it, then it's kind of weird. Then I don't understand why you wouldn't use this opportunity to have one-on-one help room session with me to resolve those issues. Okay, anyway, this is the end of lecture 21. And if you have any questions, please let me know.